Alright, in this video we're going to be looking at Lagrange error bound. And I'm hoping to give you just a little bit of background on it and quite a few examples and try to make this as simple as possible because I feel like this is kind of a misunderstood topic in AP Calculus. Not in terms of like not understanding it calculus-wise, but not understanding the difficulty because it's really not that bad. So I'm going to start you off with the idea of e to the x, right? We already know that e to the x is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the third, so on forever, and that series will converge to the value of e to the x for any x. Okay, so if we wanted to approximate the value of e, like e to the first, we'd just plug in 1 wherever we saw x. So we'd have a 1 plus a 1 plus a 1 over 2 factorial 1 to the 2, which would just be a half, and then 1 over 3 factorial times 1 to the 3, which would be a 6, and then maybe we just stopped there, okay, and just said, okay, it's approximately equal to that, and if we added it up, we'd get 2.667, which is, if you know, pretty close to the actual value of e. But we've heard that e is like 2.718, and a bunch of other decimals that doesn't have really any sort of good pattern because it's an irrational number. Okay, so that means that our approximation is off by some amount. Okay, and I'm proposing that it's off by a real number. Okay, there's some real number. There's the difference between our approximation that we did in blue and the true value of e. So we could write that. And so the value of r is kind of like the mystery here. How good is our approximation? And we're not going to ever be able to, find the value of r, because that would kind of preclude the necessity of the Taylor series in the first place. But we can get an upper bound for r using Taylor's theorem. So here it is. The Taylor's theorem with Lagrange error bound is that f is a valid approximator, or f's Taylor series is a valid approximator for f, as provided that x0 is in the interval of convergence of the Taylor series for f centered about x equals c. And it's going to be off by this remainder. And the remainder is going to be equal to the next derivative of f at some point on the interval between the centering point and the approximation point divided by the next factorial times the difference in the centering point and the approximation point to the next power for some x value z between x0 and c. Okay, and actually proving that it's going to be pretty challenging and definitely beyond the scope of this course, so that's not going to be part of this video. Okay, I'm just going to tell you what we can take away from this. Okay, first of all, that r value, that could definitely be negative, right? The next derivative, the just right value, could be negative because maybe we overestimated using a Taylor series, right? And you could see it in the formula. Either that next derivative could be negative at the magic spot, or maybe x0 is to the left of c, and n was even, so that could be a negative number. So we're going to say that the actual error is going to be the absolute value of that r, that remainder. Okay, but we can't know z because, like I said before, that would preclude the purpose of having a Taylor series if we already knew the value of the function at the point. So we're going to find a value m where the absolute value of that next derivative is less than or equal to m on the interval between x0 and c. And so we could say m is the maximum as x runs from c to x0, or x0 to c in the event that x0 is to the left of c. Okay, and of the absolute value of the next derivative. Okay, so that gives us our error bound. Error is the absolute value of r. Error is less than or equal to m over m plus 1 factorial times the absolute value of x0 minus c to the next power, because that would also, something that could be negative. So we know the absolute value will be less than this if we take make everything positive and take the maximum possible value of each thing. Okay, so what you need to know for solving problems in Cal BC about Lagrange error bound is that, you've got to start off with an nth degree polynomial centered at x equals c, and you're going to use that to approximate the value of the function, at x equals x0, some actual plug-in approximation point. Okay, then the error in that approximation will be no more than the maximum of the absolute value of the next derivative divided by the next factorial times the absolute value of x0 minus c to the next power. Okay, and I think, rather than talking to you about it in the abstract, let's get in and look at the most recent example I have for you. Okay, so most recent was 2023 BC number 6, part B. This was a Lagrange error bound problem. And I really liked this one. This one was very direct. You actually you didn't need to get any of the points in part A or part C right to be eligible for the whole thing on this. It's an entirely self-contained question, actually, if you think about it. Okay, so the fourth degree Taylor polynomial for f about x equals 0 is used to approximate f of 0.1. That's giving us all of the information that we need. The degree of the polynomial is equal to 4. It's centered around x equals 0. Okay, and it's used to approximate f of 0.1, so I know my approximation point is x0 equals 0.1. Okay, so what we want to do is we want to say, all right, error is less than or equal to, okay, it has to do with the next factorial, the next power of an absolute value, and then absolute value of the next derivative. So it would be something to the fifth power, and then f's fifth derivative. Something about the absolute value of f's fifth derivative. Okay. And then the actual values that we're going to be plugging in, it's going to be a difference between x0 and c. And it's, 0.1 minus 0 to the fifth. But what we want to do is be finding the maximum absolute value of f's fifth derivative between x equals 0 and x equals 0.1. So I might write it as a closed interval 0 to 0.1. But you want to not think about this too hard, right? If the absolute value of f's fifth derivative is less than or equal to 15 on 0 to 0.5, then it's definitely going to be less than or equal to 15 on 0 to 0.1 because 0 to 0.1 lives inside of 0 to 0.5. Okay, so I'm just going to get rid of all of this and say, okay, I'm going to take that value and plug it in the numerator. And I'll show you here in a second that that's really going to be the way to go. Oh, and they want me to show that this is within 1 over 10 to the 5. You know how we're going to do that? We're going to say that's less than 1 over 10 to the 5. I've kind of got a reason for you, but I think I'm going to, wait until we get into the scoring guidelines. If you're curious, if you're interested, I could tell you that, okay, that 15 over 5 factorial times 0.1 to the fifth is going to be, if I broke it into its factors, 5 times 3 over 5 times 4 times 3 times 2, and that 0.1 to the fifth is 1 over 10 to the fifth. And then I could cancel some stuff off and be like, okay, I've got 8 times 10 to the fifth in the denominator. That's definitely going to be less than 1 over 10 to the fifth. And that's why that works, arithmetic-wise. But we're either going to be right or we're going to be wrong based on our error bound. So, only use this like check your answer. And definitely don't not say less than 1 over 10 to the 5 if you can't figure out the arithmetic, but you are feeling good about your error bound, right? And just proclaim it, because we're not going to check your arithmetic logic. Okay, now I may have mentioned, I don't remember, I was lucky enough to be able to grade this one in the summer at the AP reading. And I remember this really opened my eyes to like how I was teaching the Lagrange error bound and inspired me to re-record this video, right? Because I think I was trying to get people to do too much. Hey, so you see, probably the model solution is really nice. They simplify it. They've shown us that that's definitely less than what we were supposed to show. Okay, but the first point is earned for either that maximum business or just the 15 over 5 factorial times 0.1 to the fifth, which is what we had. Right? We had the absolute value of 0.1 minus 0 to the fifth, but we know in AP Calculus that's equivalent. We're getting the point. Okay, so subsequent errors in simplification, that's just going to take us out of the second point. So we get the point for the form of the error bound with the right answer, right? That's the first point. To earn the second point, we have to clearly communicate this inequality. And that was kind of where the subtlety of this problem occurred, was in that communicate verb, is because of this error equals. I really want you to avoid that. That's why you're going to see me emphasize every time with these error bound problems, we're going to start with error less than or equals, whether it's Lagrange error bound or alternating series error bound. Error is less than or equal to some number, because we always talk about error bounds in Calculus BC. Okay, but what happened was students that said error bound equals 15 over 5 factorial times 0.1 to the 5 did end up earning the second point because they were communicating that the error was less than or equal to that number by saying that was a bound. But I don't want us to get into that. We're just going to go right for the answer because notice how if we did what I did suggested you do right here, that's like almost exactly what I wrote, except I had an absolute value in there, 0.1 minus 0. Error less than or equal to the Lagrange error bound, the right error bound, do it right, and less than or equal to what they said. Okay, and that's how we can get both points very easily. Moreover, it seems to be that like more and more frequently with the Lagrange error bound, they're just kind of telling you what that numerator is. What the absolute value of the next derivative is less than or equal to. Okay, that maximum possible value of the next derivative over an interval that you need. And, we have examples where we're going off a graph or a table, and I'll show you one of each of those here in this video. But I really think that this is the more common scenario. For a table example, I've got this table, and don't look too closely at it and be thinking about the average rate of change and the fact that the f and its derivatives are strictly increasing. I didn't think about this all that hard, and it might be that that's not possible, but just go with it numerically because, the table that you would be given on like an actual assessment will be accurate and possible for some function whose derivatives are doing exactly what they say in the statement of the question. All right, so use the fourth degree Taylor polynomial for f around x equals 2 to approximate f of 2.5. All right, I'm bringing the skeleton for a fourth degree Taylor polynomial, and this is kind of the point with this, is that if you get into a ridiculous situation with a Taylor polynomial, just like kind of set up the skeleton and then use your eraser. Okay, so like we're gonna replace f of 2, f prime of 2, f double prime of 2, f triple prime of 2, and f's fourth derivative at 2 with the number we're seeing from the table. So that would be at 2, 1, 5, 4, 3.5, 3. Okay, that's all we'll need. And then if we're trying to approximate f of 2.5, maybe I'll start a new line for that. F of 2.5 is going to be approximately equal to whatever I would get when I plugged 2.5 into the fourth degree Taylor polynomial, which would be 1 plus 5 times 2.5 minus 2 would be 0.5 plus 4 over 2 factorial, that would be, not something I need to simplify, but something I probably could if I needed to, squared 3.5 over 3 factorial x minus 2, oh wait, x minus 2, we know that's 0.5, cubed, and 3 over 4 factorial times 0.5 to the 4. Kind of feeling like it might have been better to just erase all those x's and replace them with 2.5s, but it's okay. I've gone this far. Hey, what I'm really here for is the Lagrange error bound to find the maximum possible error in our approximation. There are 3 key ingredients for Lagrange error bound. The degree of the polynomial we use to approximate, that was degree 4. Okay, the centering value, this polynomial is centered at x equals 2, and the approximation point x0 equals 2.5. We're always going to start off with error is less than or equal to, okay, and then we're going to have a fraction. Okay, we're going to divide by the next factorial, okay, and then the absolute value of the difference in the approximation point and the centering point to the next power, that same power, and those absolute values right there, they would not do anything because 2.5 minus 2 is positive. But you can envision, had I used a fourth degree Taylor polynomial to approximate f of 1.5, then that would have been a negative number because it had a negative number to the 5th power. And we cannot be saying error is less than or equal to a negative number because the definition of error is the absolute value of something. And the absolute value of the thing cannot be a negative number, so it certainly can't be less than or equal to a negative number. Okay, but in the numerator, I'm just going to have some m. All right, now in our head, we are thinking, well, that's probably a bad idea, like this. M is the maximum absolute value of the next derivative on the interval between 2 and 2.5. Well, I don't really have any information about 2.5 because if I did, I wouldn't need a Taylor polynomial. I do have information about f's 5th derivative on the interval 2 to 3, though. I know it goes from 1 to 2, and it's strictly increasing the whole time. So I know that the absolute value of f's fifth derivative, because f's fifth derivative is always positive on that interval, is got to be less than or equal to 2 on the interval 2 to 2.5, because it's less than or equal to 2 on the interval 2 to 3. Whoops, I wrote that wrong. 2 up to 2.5. There we go. Okay, so what we're going to do is we're going to use that 2, and we're not going to really, write all this stuff out, just get rid of it. Say, all right, done thinking. We're going to use 2 over 5 factorial times 0.5 to the 5. We could simplify that if we needed to, but we don't need to because this is AP Calculus, and we're going to stop there. And here's a graph example from my old notes book. F of 1 is approximated by the 5th degree Maclaurin polynomial for f. That first sentence has all the ingredients we need. 5th degree polynomial, n equals 5. It's centered at x equals 0 because it's a Maclaurin polynomial, and we're approximating at x0 equals 1 because we're trying to find, an approximate value of f of 1. Okay, m5 of 1 is the approximation that we would get if we plugged in x equals 1 to that 5th degree Maclaurin polynomial. What we're doing is using the Lagrange error bound to show, okay, error is less than or equal to, it's a fraction in the denominator. I've got the next factorial, absolute value of 1 minus 0 to the next power, that'll be the 6th power, and then we're going to have some m up there, where m is the maximum possible absolute value of the 6th derivative over the interval 0 to 1. Look at the picture. We've got a picture of the graph of the absolute value of the 6th derivative. What is a number that is either equal to or slightly greater than the maximum possible absolute value? There it is. It's 4. Okay, so I'm going to go in and I'm just going to say, okay, that's 4 over 6 factorial times 1 to the 6th power. And, well, we'd better hope that 4 over 6 factorial is less than 1 over 100. Okay, but if we're not sure and we just can't figure it out, we're just going to say less than 1 over 100, like I said. You just got to be confident on that. Okay, just don't let them know that you're not sure about the arithmetic, because this isn't an arithmetic class. Hey, if you're curious, 4 over 6 factorial is going to be 4 over 6 times 5 times 4 times 3 times 2. We'd start canceling some stuff off. 30 times 3 is 90, times 2 is 180. That is definitely less than 1 over 100. Okay, so that's how we could convince ourselves. Now, before we go back to the original example that we were talking about with the e to the x approximating e, I just want to point out that for the AP Calculus problems, almost always, and the other one that I have, if you're in my class, I will be showing you in class, the last one. It's an old multiple choice calculator question. On all but that one in AP Calculus, I've noticed that the number that you're supposed to put in the numerator up here is a number that is already given to you in the statement of the question. Let's go back up here to this one. Okay, this one, that 2 that we ended up using, that was a number that was given to you in the table. In the example from 2023, when they just directly gave you that maximum absolute value, it was given to you in the statement of the question. So it seems to me like they're really not trying to trick you on finding that numerator, that maximum possible absolute value of the next derivative. They're trying to know, they're trying to test, do you know the Lagrange error bound? Do you know how to work with it? And so that means that we don't need to stress too much on finding that numerator. It should be a number that's already presented to us on the page. So back to the original example about e to the x and approximating e. Okay, when we did a Taylor polynomial approximation, we were approximating for f of x equals e to the x. Okay, we used a 3rd degree polynomial. It was centered at x equals 0, and we approximated at x equals 1. Okay, that means if I'm trying to figure out what about this remainder, r, okay, that's equal to the error. And we know that error is less than or equal to the absolute value. I guess absolute value of r is equal to the error, but we don't get into that too detailed. Over the next factorial and the next power of something. And the next power is of the difference between the approximation point and the centering point. And then in the numerator of that fraction, we're going to have the next derivative's absolute value. And we're going to want to take the maximum of that over the interval 0 to 1. But because f of x equals e to the x, we know what f's 4th derivative is. That's e to the x. And the maximum possible value of e to the x over the interval 0 to 1 is just going to be e to the 1, which is e. Okay, but that presents a bit of a problem to us because we don't really know e in the first place. But I think that we know it's less than 3. Okay, and then we would, if we, were to simplify this, we would say our error is less than or equal to 1 over 8. And we can see that the error is less than 1 over 8 because 1 over 8 is 0.125. And that would be taking us to something like, I don't know, 792 maybe, I don't know, but it would definitely farther than what we need. So we see what's happening with the Lagrange error bound with the example we started with. That 1/8 is definitely larger than the error. All right, now that's all the examples I've got to show you of Lagrange error bound. At this point, you need to get out there and try it yourself. I don't want you to get too freaked out over, like, thinking it's going to be a whole bunch of questions on the AP exam. You're only going to see this once, right? Just like, other obscure topics in AP calculus where they're only going to test you on it once, like Euler's method. You're going to have to do Euler's method, multiple times. You just need to know the formula. And my recommendation now is that you just go straight for it. That you don't even try to worry yourself about getting the max absolute value thing. Just find out what that number in the numerator is supposed to be, put it in there, and then say it's less than whatever you're supposed to say it's less than. Kind of just go for it confidently, and with enough practice, you'll see that it's kind of one of those moving parts things. And if you know where the moving parts go, you can really set yourself ahead of the national average, because really, realistically, the national average for Lagrange error bound turns around and runs away scared. Okay, so we can do better than that. Good luck practicing. Thanks for watching.